Hi, my name's Neve Osullivan and I'm a third-year PhD student at the University of Oxford. And today I'm going to be talking about supergranulation in the Harps North dataset. So I'm actually surprised as I'm the first person to show this slide this week. But this is just a slide that shows the semi-amplitude of all the planets that we have a semi-amplitude for against their year of discovery. And at the bottom there, if this works, there we go. So at the bottom there, we have the signal that the Earth exerts on the Sun, which is 10 centimeters per second. Now, getting to that 10 centimeter per second level is increasingly becoming the aim of the EPRV community as we try to detect Earth twins in the RV. And you can see, up until 2010, we were making good progress at getting to that level. However, after that, we kind of stalled. And that's despite the fact that our instruments are getting better and better. Now, we probably all know the reason for this. It's because stars are incredibly variable. They're not these homogeneous balls of gases that we would absolutely love them to be. They have all these different types of variability here. We have oscillations, flares, granulation, and activity. And last but not least, supergranulation, which, despite the fact that we haven't actually talked about it today, is incredibly problematic. So this is basically all about supergranulation, as I said. So supergranulation was first discovered through Doppler imaging of the Sun. And you can see a Doppler image of the Sun there, and you can just see the supergranules kind of very clearly, especially around the edge of the disk here, less so in the center. And that's because supergranulation is predominantly a horizontal flow. It has a horizontal velocity of 200 to 300 meters per second. And when you're comparing that to the vertical flow of 20 to 30 meters per second, you can really see how this is very horizontal. It has this horizontal scale of 30 to 35 megameters. And when you compare that to granulation, which has a typical granule has a size of 1,000 kilometers, you can see how much bigger these are. It's thought to be of convective origin, though I will say we do not know much about it or the physics that underpin it. It's too big to kind of get into these simulations, so we know very little about the underlying physics. We do also know that it has some sort of magnetic element as well. We tend to see that these supergranules are kind of herded by these small-scale magnetic network. But most importantly, we found through various studies that supergranulation exerts a 0.5 to 1 meter per second RV scatter in our data. And when we're trying to get down to that 0.1 meters per second level, that's pretty big, especially because we have absolutely no activity indicators, we have no mitigation methods that we can use to kind of model the supergranulation signal in our data. So we kind of just have to treat it as white noise, which isn't great when that signal's so big. So how can we kind of start to tackle this problem? Well, we can use the solar data that we have. So this, in particular, is the Harps North solar data, taken by the Harps North Solar Telescope, which has been observing the Sun every 5 minutes when it's visible for about a decade now. And you can see that this data here is really great. It covers the previous solar maximum and goes down into the solar minimum here, and then we're going back up to the solar maximum of the solar cycle here. So we have an entire solar cycle covered, basically. And because this is solar data, we've been able to remove all the planetary signals, which means that we're left with three main types of signals in this data: the activity data, the granulation signal, and the supergranulation signal. Now, I've said we're really focused on that supergranulation and granulation signal, so we need to kind of remove that activity signal. And we do that in two ways. First of all, we use SDO. So we use HMI, the magnetogram, and the Dopplergram to basically pinpoint the magnetic areas and then find out RV variations so that we can subtract them from that solar data. And I point you to all of these works down here if you want more details on that method and the model used. And I also use a code developed by Michael Crittenier, the IARA code, which basically looks at the wavelength domain of the data and removes telluric lines, long-term magnetic activity, cosmic rays, and instrumentational effects. So those two methods leave us with data sets that look like this. So this is the magnetically active solar RVs from the Harps North data. And we just, as I said, magnetically active, they just have the activity in them. So what we do is we take our Harps North solar RVs, we subtract those magnetically active solar RVs, and we're left with these quiet solar RVs here. Ben Lakeland has a poster also on these quiet solar RVs. I really recommend you go check it out if you're interested in this kind of work and this method. Yeah. So once we've kind of got that quiet solar RVs, what do I do with it? So traditionally, we characterize those signals using a PSD, so a power spectral density in the frequency domain, and you can see an example here from Almiller et al. 2023, who combined both the HARPS North and the HARPS solar data. And we have the supergranulation signal there, and then the granulation signal there. Now, the problem with this, using a PSD to kind of disentangle these two signals, is that the knees of them, so here and here, are actually quite close together. So when we start having less good quality data or more noise, it becomes quite difficult to tell them apart. Which is why I've been using Gaussian processes in the time domain to kind of characterize these signals. So by using Gaussian processes, basically what we do is we define this data as a set as a multivariate Gaussian, and we fit the correlation between data points using a covariance matrix. So in this case, this is the covariance matrix I'm using. It's basically just a simple harmonic oscillator which has an aperiodic kind of component to it, which basically means that we see it gives a PSD very similar to what we see here. We usually model this with a Harvey law. This is basically a Harvey law, but with a different power. So yeah, it's quite a good model for it. And we just define the time period as 2 pi over that characteristic frequency, and then also the variance given by the amplitude and frequency, and some square roots. So once I have that kind of model, I go back to my quiet solar data, and I split it up into 4-week chunks like that, and I model each of those 4-week chunks independently to each other, using my Gaussian process composed of 2 of those simple harmonic oscillator terms, one for granulation and one for supergranulation. And then here are my results. So we have the granulation results on the left-hand side here, and the supergranulation results on the right-hand side. The top panels are the variance data, so log 10 of the variance in meters per second, and then on the bottom we just have log 10 of tau in days. So the SDO quiet solar results are given in pink, and then the Yara quiet solar RV results are given in green. And these vertical bars just here are the results found by Almiller et al. In 2023. So if you look at the granulation results, we see they're pretty consistent. It's pretty much what we'd expect. But when we move to the supergranulation results, we start to see these signs of a cycle. So if we look at the bottom left here, you can start to see that we seem to be having this antiphase relationship with the sunspot number over here. In this plot here, I've just kind of binned it down to 3-month chunks and then year-long chunks to be able to really see how we have that variation over the solar cycle. And we see how basically tau is getting longer as we are less magnetically active. Now, we do have this discrepancy between the Yara quiet solar results and the SDO quiet solar results. We think the reason for this is because SDO has this, the method that we're using to get our SDO quiet solar results has an area threshold, and basically we think that we're missing out these small-scale magnetic structures that we see in the sun that we know are somehow linked to supergranulation, and that's why we're having some sort of effect. However, we don't think that's the case with the Yara, so we do think there is this type of solar cycle. But if you go to the literature, you will see that while most people will agree there is some sort of solar cycle going on here, I should say this is just a table of all the studies that have looked at how supergranulation changes over a solar cycle. They all disagree with each other. There is very little consensus in the literature. Some think there's an in-phase relationship, some think there's an anti-phase relationship. And basically, we think this, again, is due to the fact that people are defining magnetic regions on the sun differently, which then leads to this huge discrepancy in the literature. So it's very confusing, and basically we need to start looking at other stars other than the sun to try and work out exactly what's going on here, and also possibly have a harmonious agreement of what magnetic fields are in the sun. But so I said we need to start looking at other stars other than the sun, and to do that we obviously need to observe supergranulation and actually be able to characterize it in other stars, which we currently haven't been able to do. So let's just see how much we actually need to be able to observe to be able to characterize supergranulation. So I've been using the Fisher information content developed by Gupta and Bedell in 2024, which is just given by that equation here. You don't have to understand it, I promise. But basically, this allows us to quantify the fractional uncertainty of a parameter as a function of the observational strategy used. So we don't need to have the y values, if you like. We just need the timestamps, and we just need the covariance matrix of the data that we're looking at. Now, because I'm just interested in the covariance and not the planets, we can get rid of that first term, and we're just looking at this kind of trace term at the second. So we need the covariance parameters, and for that I'm just using the parameters that the average ERA parameters over the entire solar cycle. So then these are the results I'm getting, and I'm aware this is a slightly confusing plot, so let's explain. On the x-axis, we have the numbers of stars we're observing per night. So we're taking a night to be 8 hours long, and we're also assuming that we have perfect weather, because let's be idealistic. So obviously, the more stars we observe, the less time we're observing each star. On the y-axis, we have the duration of the survey, which is basically how long it would take us to get down to a fractional uncertainty of 0.3% in that timescale parameter. So to get down to a vaguely precise timescale for supergranulation. And then all these different lines, different simulations we tried. So we tried each simulation 100 times, and they're just plotted on there just so you can kind of see there is a bit of range. But basically what we did is we took the 8-hour night and we split it up into 5-minute blocks. And we assume each observation we're taking of a star is 5 minutes long. And we also assume that every time we slew to a new star, we have a 5-minute overhead. So in the first case here, right at the bottom here, this kind of blue line here, we're observing a star for 5 minutes, we're having one observation, and then we're slewing to the next star, which means that we have a 50% overhead time. But you can see we can characterize 10 stars in around 20 nights when we do that. So even though we're wasting 50% of our time on overheads, we're getting a good grasp on what the supergranulation is doing because we're sampling that supergranulation timescale very well. On the other hand, if you look at the orange lines here, this is for 23 observation blocks. We're observing 23 times before we then slew to a next star. And you can see that actually we're only able to characterize supergranulation in 4 stars in 20 to 40 nights. So it's much better to observe as much as you can, but spread across the night rather than observing it all in one block. And with that, I'll just say there is a talk tomorrow by Arvind about observing supergranulations in other stars, and that's my summary.
All right, questions for Neve? Way up the back? Where's my runner? She's on her way. And Catherine, you'll tell me if there's questions online, right? Okay.
Thank you. Fantastic talk, Neve. So you talked about how the two methods that you use to clean the activity from the RVs produce slightly different results because they may not be fully accounting for the activity, but how confident are you that they are preserving the signals you want to preserve and not removing those?
So we're fairly confident that, let me go back to here just to show them. We are fairly confident that they're preserving the signals we want to observe. So for SDO, basically what it's doing is it's finding the pixels which are magnetically active and finding the RV variations due to them. It requires an area threshold, so it requires that a magnetic region be of a certain size, which is why we then lose the small-scale structure. There is a chance with the Yara we are losing some of the granulation results, but looking at the agreement of the two with the granulation signals, you can see that they're quite in agreement, so we don't think it's too bad. Yeah.
Hi, Neve. Great talk. This might be a dreaded question, but you're using a simple harmonic oscillator. Have you tried other kernel, and why did you choose an SHO?
This particular kernel, because it has a PSD that is basically the same as what we traditionally use to model granulation and supergranulation in the frequency domain. We did an entire paper that basically shows that this is a great way to model Harvey laws. in the time domain versus the frequency domain. We haven't tried other kernels, but as I said, we have done that comparison between the two different methods, and we show that we are able to differentiate between the two knees, if you like, when using this kernel. Yeah.
Down front.
Hi, Neve. Excellent talk. Apologies if I missed this, but when you were talking at the end about the number of stars and the total telescope time it requires, can you talk a little bit about what size of telescopes you're assuming here, and if this benefits more from very high signal to noise that's possible on an 8 or 10 meter telescope versus doing this on a smaller, like 3 or 4 meter telescope, where you could more easily get more access?
So here we're not really assuming anything about the telescope itself. We're just assuming a 5-minute long integration period in the observation. Using HARPS North for bright stars, that is possible. When we were observing HD 16620 for a granulation project, we were able to get granulation signal in 3 minutes in integration time. So that's possible, basically, yeah.
Awesome. Thank you.